Okay, so I know we just tested over Unit 2, but we are going to finish up the last idea that we didn't put on the test, talking about nuclear chemistry. It's really not that bad. We're going to cover basically everything you need to know on pages 22 and 23, and then we'll just finish up practicing next time on 24 with a little bit of other stuff along with it. So, jumping right in, what is nuclear chemistry? How's it different than the rest of the chemistry we've been doing? Well, nuclear chemistry focuses on changes made to the nucleus of an atom that can change the mass or identity of an element. And we talked about this at the beginning of the unit, how Dalton didn't think that atoms could change from one to the other, they couldn't be created or destroyed, but now we know they can, and it's through nuclear reactions. And there's two main types of nuclear reactions, fission and fusion. And fusion is when two or more small nuclei combine together. They fuse together to form a single nucleus of slightly greater total mass. Now, fusion is fantastic. We want to get our energy from this because there's lots of fuel available and no radioactive waste. We just don't quite have the technology right now to make this happen commercially, at least. We can make fusion happen. It just takes really, really high temperatures, which is really expensive. It's a lot of energy. So we're trying to work on perfecting something called cold fusion that doesn't need to be as hot. But either way, fusion is really the energy source of the future that we really want to be using. And the only place that it's really happening reliably and constantly is in the sun. So we're just trying to take that model and make it better, make it a little bit more contained here for us. Fission, on the other hand, is when we split big, heavy atomic nuclei into fragments, into pieces. And this can actually get a little bit out of control. This is the type of nuclear reactions going on in nuclear bombs that tends to just keep going and producing a lot of radioactive waste. And it's really hard to get. And one of the reasons why this can get so out of control is because it can cause chain reactions. The actual process of breaking down and splitting a big atom into pieces will produce more little pieces, more neutrons that can go on to hit more nuclei, make them split. So because we're starting with something that's unstable, it's breaking down into smaller pieces, there might be some other unstable bits that kind of pop off and can go and, cause trouble. So this is not what we want to have in every single person's house and car because it gets nasty, and nuclear waste is not something that you want to be anywhere close to. So there are three different major types of spontaneous radioactive decay, and this is just what we call it when an unstable isotope breaks down without any external cause or impact. It's just sitting there and all of a sudden it breaks down. That's what we call spontaneous. And we are going to be comparing and contrasting these three. So before we get into each of their own little separate areas, I just wanted to show you this quick diagram of these three main types of decay and how we protect ourselves from them, because that's really the biggest difference, is how much damage they can do to us and other materials to get to us. So I'll reference this in these next couple of slides. So our first type of decay is alpha decay. And the Greek letter alpha, which kind of looks like an A, but also kind of like a little fishy symbol almost, is the symbol we use for this. The nuclear symbol, on the other hand, generally looks like this, 4/2 He. So this is just another little helium atom that has a mass of 4 specifically, that is oftentimes released from nuclear decay. Sometimes you might see this nuclear symbol written as 4/2 alpha. As long as it's got that 4/2 part in a nuclear reaction, that is alpha decay occurring. And as we know with this nuclear symbol, the charge of a helium atom is going to be a positive 2 because it has 2 protons in that nucleus. And the size, the mass of it, is 4. That's what that nuclear symbol is designed to tell us. Its mass number over its atomic number, which tells us the protons, which determines its charge. Now, because this has such a big mass compared to the other ones, it moves fairly slowly. And that's one of the reasons, also because it's so big, that it can get stopped by just a single piece of paper. So it has the lowest penetrating power, it's the easiest to stop, and it goes the slowest. Beta decay is represented by the symbol B, or beta, and its nuclear symbol is 0/-1e-. Now, this might seem impossible. How could we have -1 protons? But if you think about it, -1 kind of means it's the opposite of +1. What's the opposite of a proton? Well, an electron. So hopefully it makes a little bit more sense why there's this E- here, because that's what beta decay is the spontaneous ejection of an electron in the process of a nuclear reaction. So sometimes, just like with alpha decay, you might see it written with that 0/-1 next to the beta symbol instead of the E symbol, but it's the same thing as long as it's 0/-1. The charge of this little electron, just like all electrons, is -1. Its size, its mass is 0, and because it's so much lighter than an alpha particle, it goes a lot faster. And that means it does make it through paper. It has kind of medium penetrating power, but it can be stopped by heavy plastic, like those plastic suits you see people wearing. Gamma decay is the Greek letter gamma, which is kind of an upside down, kind of fishy symbol looking thing. It also kind of looks like a Greek letter, or a letter Y sometimes when we write it a little bit more squished. Its nuclear symbol is 0/0 gamma, which means that it has no charge and no mass. Really, when it comes down to it, this gamma decay is just energy. It's pure energy. It's not even a particle. So it travels even faster than that little itty-bitty electron. Electrons already travel really, really fast compared to normal atoms. But gamma decay is radiation, pure and simple, so it can travel faster because it has no mass at all. And this also means that it has the highest penetrating power out of these 3 types of decay. As you saw from the previous picture, it can be stopped by lead, can also be stopped by thick concrete. So, gamma decay, while very common in nuclear reactions, is often not shown because it has no mass and no charge. It's hard to predict exactly where it's going to be until we actually see the nuclear reactions happen in real life and get to measure this gamma radiation coming off of it. So jumping onto our next page real quick, transmutation reactions are reactions that show the particles involved in converting one element to another. So this is just the written description of these nuclear changes we've been talking about in words. We're actually going to write and balance them. And what is most important to remember as you're doing this is that the mass number and the atomic number have to be balanced in order for the equation to be balanced. So let me highlight this to color code it a little bit. Okay, so in this example that you see right below these words, this is the actual transmutation reaction, and we've just kind of highlighted specific parts of it. Our mass number is all of these numbers on top, and the atomic numbers are all of these numbers on bottom. And these are going to be balanced separately, which is why we've drawn these dotted boxes around these areas. Let's say this equation, we just don't know what it makes. We know we've observed that this uranium turns into this thorium, but we don't know what else is going to be created, what type of radiation this is going to be. Well, then we can look at these mass numbers and say, okay, something that weighs 237 is turning into something that weighs 233, and we know there's something else coming out. Well, that something else has to have a mass of 4, because this arrow here where the reaction happens, no mass, no matter is going to get created or destroyed. So if we have a 237 total on this side, then the 237 still has to be my total on the other side, which is where I get that missing mass of 4. And then I look at the bottom, completely separately from the top stuff. I can see before my arrow, my atom had a mass of 92. Afterwards, the mass that I know of is a mass of 90, so there is a missing mass of 2 that must come from this other piece. And as soon as I get that 4/2, I can figure out that, oh, that must be an atom of helium, and that right there is alpha decay. So that's what we're going to be doing with these reactions, is just paying attention to and balancing the top and the bottom numbers separately. Now, real quick, in these examples, you can see that we don't always have the bottom numbers there, and that happens sometimes. In this nuclear symbol, that bottom number is the atomic number, which is a little repetitive to write since you can find it on the periodic table, but I'll go ahead and fill these in for you because it will help. And so if you ever get given equations, symbols like these, that would be my first instinct, is go fill in what you know. All right. And then my first instinct is to find the arrow and draw a line, because that's my dividing line. And then I can look at whichever side that I know everything on and use it to figure out and fill in the numbers on the side that I don't know. So right now on top, my total here is 35. So look at the other side. On top currently, I'm seeing 35 over here. So if I know my mass is going to be balancing, then that means that I have 0 more mass available for this other piece on top. On the bottom, I have 17, and -1 adds up to 16. Well, here my total on the bottom is already 16. So that means I have no other atomic number to give to this last piece. So what I'm seeing here is that this last piece is 0 over 0. And that doesn't mean that I shouldn't have a piece here. If it told me, this plus sign, that I'm missing something here, this is the mass and the atomic number that it can have, and the piece of my, the type of radiation that's 0 over 0 is gamma radiation. So this is one way that we can predict that gamma radiation would be produced. Looking at this next example, I only have one thing before the reaction. It has a mass of 229 on top. I already see my alpha decay here, which is a total of 4 on top, which means I have 225 left over for this other piece. 90 on bottom here, with 2 of that coming over into my alpha radiation, means that this is going to have a mass of 88. And this is not one of our types of decay that we've seen already, so I'm going to go look at the periodic table, find element 88, and that is radium. So I can predict that in addition to some alpha decay here, we'd also produce some radium. In this last example, we just need to take this hyphen notation and turn it into our nuclear symbol to be able to write and balance this reaction. Remember that this is our mass number, which is always the top number here. And then I can look at the periodic table in order to figure out that cobalt would have an atomic number of 27. And if this says it is undergoing alpha decay, that means this is breaking apart, and one of the pieces that it is making is that alpha decay particle. And I want to figure out what else is left over, because that can't be the whole story. It has to make something else. So we look at what we have on top before the reaction. That's 56. If 4 of that came over here into our alpha decay, I have 52 more here. 27 on the bottom, with 2 of that coming here, means this is going to be 25 on the bottom. And element number 25 is going to be manganese. So that is another daughter product that would be produced when this cobalt-56 undergoes alpha decay. So hopefully it's not too bad. It's just tying in a little bit of that nuclear symbol with some real nuclear reactions. We'll finish up those examples and go on to some more on the next pages in class. You don't have to do anything else in order to earn your stamp.